Yeah. Good afternoon, sir.
Good afternoon, Dr. Purna. Good afternoon.
Good afternoon. Good afternoon.
Good afternoon, Director Sir.
Good afternoon, Director sir. Sir, shall I start?
Yeah, very good afternoon, please.
Yeah. Good afternoon to the respected Director sir, Dr. K. Lakshmi Prasad Garu, and our dynamic principal, Dr. Sanjay Dubey Garu, and all the faculty organizers, and especially the today's participants from all over India. Sir, we have almost all 350 participants from all over India, and also we have few international participants for this, especially the 5-day extreme research methodology faculty development program on machine learning and data science. And we have identified eminent speakers from most of the technical institutions like Indian Institute of Technologies, as well as from the international universities too. In this regard, today the presenter is also joined here, Dr. Arpan Mandal. Sir, it is a privilege us to welcome you all for this 5-day FDP on machine learning and data science. So now I would like to request Dr. Director Lakshmi Prasad Garu to give a few words about this workshop. Thank you, sir.
Good afternoon and thank you, Dr. Purna. Very good afternoon to all the participants who are joining this 5-day faculty development program on machine learning and data science. Especially for the people of India and Germany, a very good afternoon to you all. And for the people who are joining from Norway, Russia and US, for all of them, a very good morning to all of them. Right? A warm welcome to you all for this 5-day faculty development program on machine learning and data science, being organized by PV Raju Institute of Technology, Narsapur, Telangana, India. First and foremost, I would like to congratulate and appreciate each and every one of you for making a decision to be a part of this faculty development program. In this era of rapid technological advancement, the importance of machine learning and data science cannot be overstated. These fields are reshaping the industries, transforming the way we live and work, and driving innovation in every aspect of our lives. By choosing to enhance your knowledge and expertise in these domains, you have definitely taken a forward step towards staying at the forefront of this transformative wave. This faculty development program is designed to provide you with a comprehensive understanding of the fundamentals of machine learning and data science, while also equipping you with the tools and techniques necessary to impart knowledge and skills effectively to your students. We will guide you through these subjects of artificial intelligence, machine learning, then data preprocessing, predictive modeling, deep learning, natural language processing, and many more during these 5 days. And the expertise in all these subjects will definitely drive you more effectively in dealing with your routine, regular, the classworks, and also the research work which you are undertaking. And I request you all to interact with all the eminent experts we have chosen in their field, to interact freely with them, and then try to acquire as much as knowledge possible during these 5 days. Apart from, it's not just the theoretical knowledge which we wish to really present you. Apart from the theoretical knowledge, we have planned sessions actually to you to really take you to the hands-on learning and to really make you to understand the tools in these basically areas, so that this can be really taken up further. But at the same time, I really caution you all that just mere attending to this 5-day program may not be fully sufficient to you. As faculty members, we need to be updated continuously, and that updation is a must actually, especially in the continuously growing artificial intelligence, machine learning, and data science areas. Because these subjects are still evolving and there's a lot of scope for continuous development. So unless we are continuously updating ourselves, we will not become relevant in these areas. And at the same time, kindly think in that growth mindset and really present yourself and see that your full time is utilized for more and more learning. And we provide you for that excellent, rich learning experience over these 5 days. We have eminent experts like Dr. Arpan Mandal from University of Southampton, UK, and we have Dr. Samit Biswas of Indian Institute of Science, Engineering and Technology, Calcutta, and we have Dr. Arpan Garai from Indian Institute of Technology, Delhi, and we have Dr. Mayuk Sarkar from National Institute of Technology, Jamshedpur, and Dr. Garima Shakya from the Kyushu University, Japan, apart from the in-house faculty who is having complete expertise on these areas. And I welcome you all once again to basically this 5-day faculty development program which is organized by basically the computer science and engineering, and more focusedly the artificial intelligence and data science program, and then data science program and artificial intelligence and machine learning programs. And I am sure that this journey of these 5 days will be fruitful and a wonderful, enriching experience to all of you. Thank you. Thank you so much for giving me this opportunity. Thank you.
Thank you. Thank you so much for sir for your valuable suggestions and the insightful thought process and what actually as the program we need to take away. Okay, so for explain in a detailed way. So now I would like to request our dynamic principal, Dr. Sanjay Dubey garu to give the addressing.
Thank you, Dr. Kurna. It's indeed my pleasure to be part of this program. And as a convener of this, one of the convener of this program, I'm very much happy to be associated with this. So, distinguished guests and speakers of this 5-day FDP program on machine learning and data science, my honorable director sir, my faculty members, and most importantly, all of the dear participants of this 5-day FDP. So learning new skills that is filled with, of course, immense pride and excitement needs to be there from your side also. So it's my privilege to welcome you all to this transformative journey that will equip us with tools, knowledge, and navigate the landscape of AI. So as you all know, machine learning and data science have been emerging driving forces, giving revolutionary breakthroughs across various industries, right from if you talk healthcare or finance, transport or entertainment. The impact of these fields is very much undeniable, as everyone would agree with me. So as an educators and researchers, it is our primary responsibility to keep pace with these advancements and nurture the next generation of data scientists or machine learning experts. So I am excited to see over the next 5 days, we have curated the program in such a way that I should thank all the organizers and my co-conveners who have curated this content in a way such that you will go through the principal methodologies and applications of machine learning and data science. Apart from that, it is a combination of both hands-on and lectures. And this we only did it to aim to foster an environment of interactive learning as well as knowledge sharing. I'm sure that based on the schedule that it might be shared with you, I'm happy to say that we have experts from Southampton University covering large language models. We also have experts in the area of machine learning and deep learning, as well as we are also touching mechanism of design for resource allocation and support vector machine and so on, which you will come across. However, this FDP is not merely about acquiring technical expertise only, but we also aim to take all the participants to build an opportunity as take this as an opportunity and build a vibrant community which would have scholars, educators, and as well as practitioners. So this connection will definitely, I'm sure that this will foster more new collaborations in new ideas, and also stimulate interdisciplinary projects. So let us take the advantage of this platform to engage and have meaningful conversation, and which would ignite definitely spark of creativity within ourselves and each other. Finally, to all the participants, I would urge you to embrace this opportunity with enthusiasm and with a growth mindset, and seize every moment that you learn and ask questions, explore the boundaries of or to whatever potential you have. Remember that this learning is a lifelong journey, and program is just a beginning for the exciting adventure. So once again, I extend warm welcome to all of you, and also thank all the speakers who have joined online today and who will be joining in the next 4 days with an unwavering commitment to excellence and collaboration. So we together let us shape the future of AI and build a better world. Thank you for this opportunity.
Thank you, sir. Thank you very much for your deep and most analytical case studies you have explained about. So definitely we'll promise from all our organizations as well as from all the speakers. These 5 days will be definitely fruitful and useful for all of the participants who have joined from the different origins of India. So without further delay, I would like to invite our today's guest, the speaker, Dr. Arpan Mandal. Dr. Arpan Mandal is a dedicated researcher and academic professional, currently working as a research associate at University of Southampton, UK. He has completed his Bachelor of Science honors with computer science from Ramakrishna Residential College, Narendrapur. And he has had double PGs post-graduation. One is from Pondicherry University. Later on, he has done his Master of Technology in Computer Science and Engineering from Kalyani Government Engineering College, Kalyani. And he has started his PhD, the journey of his PhD from Computer Science Engineering, Indian Institute of Engineering, Science and Technology, Shibpur in 2022. Mainly his research focused on advancing the understanding the application of cutting edge technologies in the field, contributing to the body of knowledge in his area of expertise. During his time, he has published many of the reputed articles in the reputed journals. So his main interest research are focused on few short learning, natural language processing, and legal data analytics. His contributions are developing some unsupervised approaches for measuring textual similarity between legal court case reports and a sequence labeling model for catchphrase identification from legal case documents. So recently, from the recent articles also, so there is a lot of research is going on legal data analytics. We're very fortunate to have him here today. And beyond his research achievements, Arpan has actively participated in various academic and organizational activities. He has organized some workshops, including international conference on computational intelligence in pattern recognition. It is one of the famous conference for the computer science engineering people, especially in the domains of AI and data science at IIT Shivpur. And later on, he has coordinated for the workshop called as Forum for Information Retrieval Evolution, called as FIRE 2005. So it demonstrates his able to his commitment and knowledge and dissemination and fostering collaboration among different researchers. He has actively contributed to the projects and at renowned institutions, including IIT Kharagpur, where he has working under the project title Smart Legal Consultant. It is an AI-based legal analytics agent. Later on, Arpan's research endeavors have been recognized and supported by esteemed funding agencies. Currently, he's doing his research by a funding organization, UK Research and Innovation, UCRI, focuses on the reduction of shortening on social media under the ProTech Theme 2.0 project. Moreover, his PhD studies were funded by MITI, Ministry of Electronics and Information Technology, Government of India, under the prestigious Vishwesvaraya PhD scheme for Electronics and Information Technology, reflecting his academic excellence and research potential. As he continues his research at the University of Southampton, he remains too dedicated in pushing the boundaries of knowledge, making significant contributions in the field of artificial intelligence and in the application of legal domain and beyond. So we are very privileged to have you here, sir. So welcome to the
Thank you.
5-day.
Thank you very much for your kind words. I mean, that was kind of an overstatement, actually. But it's I do not work in the legal field anymore, but it's related to criminology and stuff. So today we'll not be discussing about any legal stuff, but the core part of natural language processing.
Thank you, sir.
Okay, so shall I begin then my presentation?
Yeah. So thank you, sir.
Uh,
Thanks, sir.
Thank you everyone for your kind words. Thank you, Director Sir. Thank you, Principal Sir, and thank you all the organizers. Is my audio clear, loud and clear? Okay. So let's start with today's presentation. Okay, so are my slides visible now? No?
Not yet, sir. Just it is loading now.
Okay. Okay, let me share my screen instead. Okay. Okay, I think my screen is at least visible now, is it? Hello? Is my screen visible now?
Yes,
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 yes.
sir.
Yes, sir.
Okay. Okay. So I am Dr. Arpan Mandal, and I'm a research associate at University of Southampton. So my work closely deals with building safeguarding policies for children to safeguard children's privacies online, especially on social media, and using texts and large language models. So today we'll be discussing about large language models, its past, present, and future. Okay. Before beginning this talk, maybe if I just mention the uh, biggest example of large language models would be uh, ChatGPT, which probably everyone has heard of. So before beginning, let's have a brief overview of what are the contents of our discussion today. So first, we will look at what is natural language processing. I mean, the brief overview, including the definition itself. Then we will look at what are some kind of tasks that we solve using natural language processing. Then we'll look at what are large language models. And so to understand the current state of the art models, first we'll go through a brief history. So how it evolved from just the basic uh, statistical models to current neural network models. So we'll go through that. And then we'll look at what are the performances and what kind of models are built today. We'll also go through what are some of its shortcomings and also how we can improve them. And lastly, we will also have a live demo of 13 billion parameter model. So this is a large language model, which is now possible for us to run it locally. So I'll be running it on my laptop. So that's quite exciting. And it's quite exciting time to live actually. So yeah, and lastly, we'll look at the conclusions and future directions for large language models. Its potential danger for society and what steps can we take, things like that. Okay, and then we can have some question answering session, of course. So I encourage everyone to take notes of what are the doubts that you're facing during the talk, so that you can ask me at the end of the session. Okay, so what is natural language processing? It's it's a field of artificial intelligence which focuses on interaction between computers and natural language. So that's the most simple definition that you can have. So it's a field of AI which deals with textual data, language. Okay, what do developers or researchers do in this field? They develop algorithms or models or techniques that enable a computer to understand the text, the meaning of it, or classify certain kind of text, or extract important portions from the text, which would be very much task specific. And we can also generate new natural language. So the model will be able to write on its own. Okay, let's look at some of the tasks that we perform in NLP. So these are very traditional tasks, and the list is not exhaustive at all. There are many more tasks. So I have chosen some generic tasks to give you an idea about what we do in NLP. So we have text understanding tasks such as entailment. So these tasks require the model to understand what the core idea and the logic is present in the sentence or input text. So in entailment task, what we have is we have two inputs. We have the premise and a hypothesis. So hypothesis is just a statement, which is basically a sentence. And the task is, given the premise, we have to decide if or not it is provable. Okay. So if the information of the hypothesis, the statement, is present in the premise, and if it's true or not. Okay. And The second task is extracting dependency graphs based on grammar. So this is very much dependent on the language we have. Uh, but this is kind of an intermediate task, but also requires the model to understand the language. It's a more traditional, but this task has become more obsolete nowadays because we have much more advanced models. We don't, so this is not the final task. This is one of the intermediate tasks. So that's why we do not need it now. Uh, Among text classification tasks, we have actually a number of tasks. So I have chosen just sentiment analysis and detecting spam messages. So detection of spam messages is pretty much self-explanatory. What you do is you filter emails or messages on platforms where the platform can employ certain algorithms to detect spam messages and filter it out of your main inboxes. So Gmail or Outlook, they already have these filters. Of course, they use large language models nowadays. Uh, and for sentiment analysis, the task is to determine whether the input is more positive or negative. Um, Say, for example, we have product reviews or movie reviews, and the company wants to know what kind of reviews it's getting from the customers. So they are going to analyze each and every review, and they are going to assign some score of how much critical has the review been, or how much appreciative has it been. So how much positive or negative. Language translation is a pretty important task, which has been handled recently very well. And the large language models perform very well in translation of natural language. So the task is to translate an input sentence or two sentences, so input text from the source language to a target language. Information extraction is often overlooked, but it's one of the most important tasks in NLP, I suppose. Keyword extraction is one of those tasks where when you're given a document or a long input text, which is probably hard to read or time consuming to go through, you extract certain number of keywords or key phrases which supposedly should give the main idea about what the document is. Okay, so that is one of the core tasks, and it's very subjective actually. So there is no definite answer for keywords. So that's why it's very hard to evaluate how the performance of the model is. So one of the key tasks in my doctoral program was keywords extraction from legal documents. And yeah, so that was one of the challenge. Entity extraction is another challenge where we need to extract dates or locations or persons or organizations from the input text. And this is important when we have issues like we have to um, ex let's say we have a question answering machine where we ask um, in uh, which organizations did you work in the past? If the machine has to understand this question and answer this question, they have to actually go through all the entities that are present in the input. Okay, given that the input contains the answer. So that brings me to question answering. So this is one task which is also excelled by the large language models nowadays. So traditionally, the task has two inputs. Although nowadays we just give the question and expect it to answer, but the traditional way is to just not just give the question, but also accompany it with a paragraph or a passage. Okay, so that that passage or paragraph contains the answer, and the task is for the language model to answer the question. And lastly, we have text generation. This part of NLP was not very much possible until 2017, I would say, because it was very hard for a model to generate new text. But recently, it has excelled quite a lot in this field. Tasks in this text generation kind of tasks, we have abstractive summarization, where again we have it's more or less like keyword extraction, but it's built of complete sentences. Uh, and it's abstractive, which means you cannot just take up or cut away, extract portions from the input text. You have to write it in your own words. You have to summarize a given long text, be it document or a paragraph, in your own words. Mm, so that is one of the toughest challenge, and the research is going on hard this way. Um, and then we have dialogue systems. So these are mainly used by corporates, where you can call them chatbots even. So these are basically automated replying systems where um, there are certain frequently asked questions kind of response give fed into these dialogue systems. But nowadays, it can actually understand your question and take you directly to um, what you intend to ask for without going through all of the unnecessary questions that we used to solve it, for example, in an automated caller facility. Okay, then we have creative writing. This is one of the biggest achievements of language models, probably. That's the USP for ChatGPT because it is a commercial system after all. So it can write poems for you, it can write storylines for you, and that is amazing. That is amazing. Um, so let's start with language models. What is a language model? Quite simply put in just a sentence, a language model is an algorithmic way of providing a probability distribution over words or word sequences in a given context. Okay, uh, I should tell you this. Most parts of the talk that I'll be giving today is completely non-technical, and I have deliberately kept it that way so that you can still get away with some concepts you can understand. I understand not everybody is from a computer science background. I might be wrong on that, but yeah, so most of the parts in this talk is pretty non-technical. So what do I mean by, so let's come back to language model. What do I mean by algorithmic way of providing a probability distribution over words or word sequences? And that too in a given context. So this context has to be given. You cannot just generate anything. Okay. So what is the context and I mean, how do we generate this probability distribution? A context is like, let's say you provide, you have this sentence or phrase, all the very best, okay? But you remove the last word best and you have all the very blank. And now the language model has to predict uh, which word should be appropriate that should fill in this blank, okay? For that, what it has to do is it has to assign a probability score to all the possible words in the vocabulary. So for vocabulary, you can imagine all the possible words in the dictionary and some other colloquial words as well. Um, so it has to assign all of the words a probability in a way so that the word best is given the highest probability. And that's very tough because vocabularies or dictionaries with colloquial languages um, has more than 50,000, at least 50,000 words in it. Uh, and oftentimes the language models are not very good at it, but it still performs very good. It might not come up with the best answer, the best word, but yes. So what are the traditional statistical models? So we have traditionally we used statistical models, but recently we use neural network models. Among statistical models, some famous ones are TF-IDF, uh, which is a very frequency-based model. Uh, and we try to count the occurrence of each word to determine a score, which we call TF-IDF, okay, on n-grams. And we have hidden Markov models. You might have heard its name. Uh, it's still a statistical model and it performs quite well. But a predecessor to this hidden Markov models is conditional random fields. Conditional random fields actually performs quite well, even uh, even if it's not a neural network model, but it still performs quite well. And among neural network models, we have LSTM or GRU. They were very famous. And these LSTM and GRU are also called recurrent neural networks. Okay, so there are many kinds of recurrent neural networks, and we'll come to that. And the next form of models are based on transformers, and we have BERT, GPT, ChatGPT, and BARD. Okay, so these all models are built on transformers. In fact, all of the models that we have recently that perform quite good are built on transformers. Okay, so let's start with the most basic and intuitive form of language model, which we called count frequency. So in the earlier slide, I talked about TF-IDF. Okay, so the part TF means term frequency. Okay, that is somewhat similar to count frequency. And what is count frequency? So basically, we have to assign a probability to a word. I mean, how likely it is to fill up the blank. So that is the question we have to answer. How likely uh, this word is to fill up the blank, and the next word is to fill up the blank, and like that. So we'll assign probability scores to all of the words. Okay, so let's say we are assigning probability to the word chocolate. Okay, and we have the context. We have this like word before chocolate. So, the question is assign a probability to the word chocolate given the context like, which is very simply, it's very intuitive. You count the number of these words occurring together in a given set of data. So we need a set of, say, 50,000 documents. Hmm? And from there, we literally count like how many times does like chocolate occur in those 50,000 documents. So that's a large set of text, and we count how many times does it occur and divide it by the count of chocolate. Okay, so the numerator is how many times does chocolate occur after the word like, and the denominator is how many times does the word chocolate occur at all. Okay, so that's very intuitive, and but this has one obvious drawback, like the context uses only a single word, which is like in this case. So we're not considering the words before that, and that should be able to affect uh, the probability of the word chocolate. To tackle this problem, we can just simply extend the context. Like instead of using just one word like, we can use kids like chocolate. Okay. Uh, but still, so here what we're doing is instead of the counting like chocolate, we'll be counting kids like chocolate and dividing it by the number of times chocolate occurs on its own or anywhere else. Okay. So we can keep increasing this number n. So this kids like chocolate, uh, a sequence of three words is called 3-gram or trigram. The sequence of two words, it's called bigram or 2-gram. So we can call it an n-gram where n denotes the number of words in the word sequence. Okay. The problem is we cannot increase n indefinitely because you can imagine you have to store these count values beforehand before calculating this probability. So to score this count values, you can imagine if we increase the n, the number of distinct sequences that are possible with say 4 words or 5 words would be huge. And they would be so huge. In a practical standpoint, I would say if you go beyond n equals 7 or maximum 10 or 12, that's it. After that, you don't have any more feasible power in your uh, machines nowadays. Um, especially the memory requirements to score that number of count values. So increasing n increases space complexity to an amount where it's not feasible anymore. So the next solution comes is recurrent neural networks. Uh, and the most prominent recurrent neural networks would be LSTMs and GRU. LSTM came in 1997 and GRU came in 2014. Okay. So what's the working principle? So I'm not going into the detailed architecture of recurrent neural networks. Again, it has a very uh, not so easy to understand architecture. So I'll just give you the gist of the working principle, okay? So instead of using n-grams that we are using, we use a hidden representation. What is a hidden representation? It's a set of numbers, okay? The number is meaningful, not to us, to the machine, but it uses a fixed size of hidden representation. And this fixed size is the key because the machine can now store information from long before, from a context long before, um, and it can still represent it within a fixed size of hidden representation. So the machine now somehow has to generate this hidden representation. How do we do that? Simply by using a neural network, a special form of neural network. So that is LSTM or GRU. They actually go word by word, scan word by word, and at each step they try to generate a new hidden representation. Okay. So as you can understand, this is a sequential form of processing hidden representation, but the problem still lies. The range of context is still short. I mean, still not enough long to represent every probabilities correctly. Okay, so let's take this example for a second. So let's say we have this input. I grew up in France, and when I was younger, I used to regularly run to the shops to buy fresh baguettes for breakfast. I speak fluent blank. Okay, so we have to fill in this question mark. What do you think as a human would it fill this question mark? Of course, I grew up in France, so I would be able to speak fluent French. But for the machine to understand this, it has to go back a number of words back and it has to understand. So this is the word that determines the word French. That is hard. That is pretty hard because it actually has to ignore this entire sentence in between because it doesn't give any idea about what the word should be in this blank, isn't it? But it's not going to be the case for every input. So that is a problem. So how do we solve that? Using attention. So what is attention? It's still using the fixed size of hidden representation, and it can be used with existing models. Just uh, huh. Am I not being audible? Is this not audible? Uh, I just got a call saying I'm not
Sir.
audible.
Yes, sir. Audible.
Okay. তুমি পাচ্ছ না আমি তো এখানে জিজ্ঞেস করলাম লোকে বলছে হ্যাঁ yes it's audible. Okay. Okay. So anyway, so as I was saying, so what is attention? So we were talking about why it is hard for the neural network, so the recurrent neural network to attain to this this word, okay? And what's happening. Just a moment. Yes. Okay. Let me get the point. Okay. So we are still using the same hidden representation, but it's instead of focusing on every previous word as we did, we will now be focusing selectively on certain words that we feel is important. I mean, not we, the language model feels important. The attention mechanism feels important. So in this case, it will assign more importance or more attention to the word France. And it has to learn to do that. So it also needs to be trained along with the LSTM or GRU that you are using. Okay. And it somehow learns that. And the context is now larger because it can now understand that these words doesn't make sense. So I'm not going to I'm not going to store these informations in the hidden representation. I would instead store this information in the hidden representation more than these informations. Okay, so now it's easier for the model to predict the blank word. Now comes transformers. Why? Because in LSTMs, they were still processing in a sequential fashion. Okay, uh, in the paper, the paper of transformers is titled "Attention is all we need." What it means is you don't need a recurrent neural network anymore. You can just stack attention models on top of each other, and you can still get good performance. Okay. And the paper was famously written by Vaswani et al. Vaswani is an Indian writer, and definitely, although the paper is titled "Attention is all we need," he is not getting all the attention he needs. And I think as Indians, it's our duty to put him up front in front of the media because he's not getting all the attention. And mind it, transformers is the base model upon which all the large language models, today's models, are based on. So this is the transformative paper that we had in the research field. Okay, it came in 2017. It was initially built for natural language translation, so translating from a source language to a target language. And famous models that are built on top of transformers are BERT and GPT, and other models as well. These are the basic architectures. By the way, ChatGPT is built on GPT, so it's built on transformers as well. So this is the basic architecture. I'll not try to make you understand every inch and bit of this diagram. I'll just give you an overview. Okay, so this is the place, if you can see my pointer, this is the place where the input goes in and it processes the input parallelly. By that, I mean it doesn't have to scan each word sequentially. It processes every word once at a time. Okay, and this red box, we call it an encoder. And this blue box, we called it a decoder. The task of the encoder is to form the hidden representation. Okay, and the task of the blue box is to generate the new word. Okay, and the encoder, although this processes the input everything at a time and parallelly, but the decoder, this has to produce words one word at a time. Okay, it cannot produce every word parallelly. And the working principle is similar. So it has a hidden representation that the encoder is forming mainly. And the key component is attention. That's the only component that it needs. And this allows for a much larger context. And because as you can see, every word is being processed parallelly. So it can attain to every word equally whenever it's needed. Okay. But there lies a problem, which is limited input sequence length, which is still prevalent in these language models because they are all built on top of transformers. So this problem has not been dealt with properly. And we the problem of input sequence length is because of this attention mechanism. Okay, so if we increase the input length, the model complexity increases in, I mean, it causes the model to get much larger. Okay, so which is not feasible for every computer to run. Okay, the training or run the model. So this is the actual architecture of the BERT model. So the encoder that I showed you in the previous slide, we have 6 encoders stacked on top of each other. So the input of the next encoder is the output of the previous encoder. And after we encode and form a hidden representation, we pass that hidden representation to each of the 6 decoders, which are also stacked on top of each other. Okay, so we pass this input, which is probably French, and we pass the hidden representation to the decoder, and the decoder doesn't generate the output all at once. It has to generate word by word. Okay, and so for the first word, it generates I, and this output is again fed into the input of the decoder, and the hidden representation is available all along, okay, throughout the generation process. And we have I am generated next, and again I am is fed into the decoder input. Then we have I am a, then we have I am a student. So that's the, and how do we know where to end? So we have a special token to denote that this is the end of generation. We need not generate more output now. Okay, so that is how we do it. So yes, so one important distinction between encoder and decoder is encoder processes inputs parallelly, but the decoder produces words sequentially. Let's go and look at BERT architecture. BERT architecture is basically the same as transformers, except instead of decoders, they remove the decoder part. And instead of using 6 encoders, they use 12 stacks of encoders. Okay. So what's the benefit of it? The straightforward answer is the entire process now becomes parallel. So can the model perform good without the decoders? Yes, it cannot generate much language, like the decoders were used to generate the specific words, but BERT cannot generate very well the words, but it can form a very good representation of the input text. And using that, we can solve a number of tasks. Let's say the task that we discussed about sentiment analysis. Okay, so the task is not to generate new word, it was to identify whether a product review was positive or negative. Those kind of tasks are called classification tasks. They can be done very well by BERT architecture. Okay, so the model came in 2019, and we trained one of our BERT using Indian legal documents. You can look it up on Hugging Face, the link I've given below. So it used 25 gigabytes of Indian legal documents. You can check that out. Just like transformer encoders, it processes the input in parallel. I already said that. So, okay. So to use BERT, so to train BERT, so to make the model usable, we have 2 steps. We have pre-training, okay, and then we have fine-tuning. So the pre-training part is the time-taking part. It requires the most infrastructure, it requires the most time and cost. This is already done by Google, okay? Although you can do it yourself, but it takes a lot of time. And this is the part where the model is given a specific task of pre-training task, which we'll discuss in the next slide. And then once this model is ready, this is very close to solving the given task. We just add a specific, a very shallow neural network on top of BERT, okay? And then we fine tune it. The fine tuning process is on a given task. The fine tuning process is basically learning similarly to pre-training, but using a different task-specific output layer. So that is the last layer, okay? So we're changing that, and we are training it on a specific task, like NER is named entity recognition. So the entity recognition task that we talk about, okay? So what are the pre-training tasks? So this is the most important part, because you can do this afterwards and given any pre-trained model, okay? So the pre-training task of BERT. Okay. So the pre-training task, BERT has two pre-training tasks. One is masked language modeling, and the second is next sentence prediction. Okay. Do not confuse this term language modeling with language models, because as you can see, it's modeling. Okay. So this is the way that language models are created. This is not the language model itself. Masked language modeling is basically very simple. You have an input, typically a sentence, and you mask out a specific word out of the sentence. So this is the blank space that we need to predict. Okay. So if we have all the mask best, so in place of this mask, the model has to predict the word very. How does it do it? So we have a set of words, let's say a set of dictionary words. Okay. Okay. Anyway, I think somebody is not muting his microphone. Anyway, so to fill in this blank using very, what we do is we assign probability to all words in the vocabulary, and we expect that the word very would have the highest probability. And of course, the language model at first doesn't have any idea. So it starts guessing, and once it gets wrong, the language model is trained. That is how the longest model becomes powerful after many iterations of training. Okay. The next sentence prediction task is very simple, but I think the term next sentence prediction means you have to predict the next sentence, but that's not at all the case. The task is much simpler. You have two sentences as input, and you have to determine, I mean, the language model has to determine if the second sentence actually follows the sentence one. Okay. So if we have this example, I have a class, and sentence two is I'll be back by 6. Yes, it probably is the next sentence. Sentence one, if I have a class and the sentence two is completely unrelated, is of course not the next sentence. Okay. So these are the two tasks that BERT is pre-trained on, and they release the model. And then as we want to use it, we have to fine tune it on another target task. Okay. After BERT, we have GPT. So GPT came in 2018. Towards the end of 18, you can say 2019 even. Anyway, so GPT stands for Generative Pre-trained Transformers. And instead of encoders, it uses decoders. And again, 12 stacks of transformer decoders. Okay, it's so if you remember, decoders used to generate words sequentially, word by word. So to pre-train, so this also need pre-training and fine-tuning, just like BERT. So to pre-train, we cannot use masked language modeling, because masked language modeling requires to predict the word anywhere in the sentence. Okay, but GPT can only predict the last word given all of the words in front. That is, all of the left side words, we have to predict the last word. And that's why they gave the pre-training task a pretty name, which is causal language modeling. It's just a fancy name of masked language modeling to predict just the last word. Okay, it's very much similar. So instead of using the word in between, we are just masking the last word, and it has to predict this. GPT-2, so this was the first version of GPT-2, GPT, and GPT-2 has, after we pre-train, it has another pre-training task which uses meta learning. So you don't need to understand what meta learning is. Basically, it is fine-tuned on several data-rich tasks, supervised tasks. So, um, so So they are trained on existing tasks for which we have data for, like named entity recognition, like sentiment analysis, and so and so. It is also trained on those things before releasing the model itself. So they're considering that part of pre-training. Okay. Okay. So the model sizes of the language models are increasing exponentially with time. If you look at this graph, you can see the y-axis is in a logarithmic scale. Okay. It increases 10 times after each step. And you can see the size of the language models increases almost linearly in a logarithmic scale. Okay, it's basically exponentially increasing with time. So this is the BERT model, which has 340 million parameters. Okay, and we have GPT-2 here. The GPT first version is very close to BERT because it has 12 stacks of decoder instead of encoders, so they have pretty similar uh, number of parameters. Then we have other models, and then we have GPT-3, which is more than 10 times the GPT-2. So it is an order of magnitude higher, we say. Okay. And GPT, the number of parameters in GPT-3 is the number of parameters in ChatGPT. Okay. So this performs quite well. So although it's not the same as ChatGPT because the architecture is different, the architecture is called Instruct GPT. It's built on a different architecture, but it has the same number of parameters. Okay. And now, early this year, we have GPT-4, which is not plotted in this graph, but it also follows along this red line. Okay. It has parameters in the range of tens of trillions, and that's really huge. And all of these models are available, not all of these models, the open source models like BERT, uh, GPT, GPT, I think GPT-3 is also available on Hugging Face. Hugging Face is a very popular online store for distributing language models based on transformers. So they have their own Python library, and the library is called transformers. So yes, you can check the uh, website out, and you can download your models from there. So as you see, the model sizes increases with time, and since GPT-3, the model sizes were very much infeasible for fine-tuning it on a workstation or a local machine. Okay, so for fine-tuning, what we did was, if you forget about prompting, so fine-tuning, what you did was you had to modify each of those parameters. Let's say BERT has 340 million parameters. To fine-tune that, we had to change and tune each of the 340 million parameters. And for that, we need to store the model entirely on some memory. Okay. And these later models after GPT-3, the models were so large that it was not feasible for uh, I mean, local machine to do this job. You cannot just store that much amount of memory. Okay. And so something called prompting came into the research field. Okay. Prompting is also called priming. So the prompt is basically an instruction to perform the job. So let's say we want to do some sentiment analysis. We actually tell the model, perform sentiment analysis on this input or something similar. Okay. So that instruction might vary. And that's where this prompt engineering comes. Okay. So it's the humans who have to engineer prompts. Good prompts give good results. And uh, we have these 4 types of prompting. Okay. What are those? Those are zero-shot prompts, one-shot or few-shot prompts, and chain of thought prompts. Okay. And we also have artificial prompts or prompt tuning. So let's look at what those are. So this is an example of zero-shot prompt. So we basically give the task or input, and it is expected to give the output. Okay. So this is a task of question answering. Of course, we give it the question, how does the sun work? And it gives us the answer. The sun works by fusing hydrogen nuclei together to form helium and so and so. Okay. So let's look at a few examples of how zero-shot prompts look like in different tasks, not just question answering tasks. So we have this different tasks like sentiment analysis. If you consider sentiment analysis, you have this input. I love this movie. So that's the movie review. Say, generally reviews are longer than just a sentence or just a few words, but still for this example, let's consider this is the input and this is the template. So in place of X, you put the input. Okay. So the input would be I love this movie, and then the movie is Z. So Z is the blank word that it has to predict. The language model has to predict. And the possible answers would be great, fantastic. So these are the positive reviews. And we can also have negative words. And we can measure the probability assigned to these words. Okay. And that is how we perform zero-shot prompting. So we give the model and we check which of the words are generated, and we likewise do the so it performs the job like that. Next comes one-shot prompting. What is one-shot prompting? So we basically give the model to understand. We give the model an example of how to perform the job. So we give the instruction. Let's say I need short bullet point answers to my questions. So this is the task description. So if we only gave this one, it would have been zero-shot prompting. And we also give this an example, okay, of how to solve the problem. So we give it an example like we give a question, how does the sun work? And the answer is given in bullet points, fusing of hydrogen nuclei to form helium and so and so. And then we give the actual question we need the answer for. And then the model generates the answer for us. Okay. That's how one shot. And for few shot is very similar. Instead of just one example, you give a few examples in the terms of like 5, 6, or 10s, whatever can fit into the uh, input sequence length limit. Okay. And there's this interesting kind of prompting where we have chain of thought prompting. Although this kind of prompting is not applicable to all of the tasks, um, a few of the tasks can use this. Like let's say we have specific requirements. The input is like this. Take the last letters in the words Zeitgeist and AI and concatenate them. And we answer with an explanation, okay, with an explanation of how we are getting the answer. So we answer the last letter in the word Zeitgeist is T, the last letter in the word AI is I. So if concatenated, they become TI. The answer must be TI. Now we give the actual question, which is take the last 2 letters of 1 and 2 and concatenate them. So the machine generates this answer, which is pretty good. The last 2 letters of 1 are NE, the last 2 letters of 2 are WO. Concatenating them gives NEWO. The answer must be NEWO, which is a very good answer in on itself. But if we want to modify this, I think this is unnecessary, but still do this again, but drop any spacing and see it can actually do that. And it's amazing how it can remember what it generated by itself. It can remember what the instructions we gave it first and still do this modification, and it does it correctly now. Okay, it removes the space this time. And all of this is coming from the stack of transformer decoders. Okay, so in the chat GPT, instead of 12 stacks, they're using 96 stacks. Okay, and that's huge, and it's much wider. The input sequence length is, I think, 12,288, if I'm not wrong. It's more than 12,000, by the way. So that's huge. And there's this last type of prompting called auto prompting. So here we do not provide any actual words. So the exact details are out of scope of the talk because I promised to keep it non-technical. So instead of giving actual words as a prompt or as the instruction, we provide pseudo words or numbers. Basically, we provide a sequence of numbers, which we call embeddings, that are tuned to provide the best representation of the instruction, so that the model is now not restricted to the words that we give as instruction. We can represent the instruction itself. I mean, how to do the job, we can say that to the model using numbers. It's internal representation system. We can do that. And it can be done automatically. So no humans has to generate those instructions. And that's interesting. So let's look at the history of large language models. In 2017, this is a timeline. In 2017, we have the transformer models, the breakthrough I was talking about, and nobody talks about Vaswani, and that's sad. 2018 came BERT and GPT. These were two revolutionary language models. And 2019 came GPT-2. It is basically GPT with that newer meta learning pre-training task. And it's also a larger model, much larger model. And it's also trained using a much larger set of data. Okay. GPT-3 is very similar to GPT-2. It's a much larger model, and it also trained using, again, much larger data than GPT-2. Okay. Excuse me. Okay. Then comes DALI. DALI is a multimodal model. So it inputs text, but it outputs images. So we call them multimodal models. Okay. Stable diffusion is another multimodal models which creates very high quality images given an input text. So you might have seen a recent search in AI art on social media. So most of them are created using either stable diffusion or something similar. DALI is not on par with the quality of stable diffusion because it's a larger model. And we have then ChatGPT. Everyone knows about that. So it's a collaboration. So it's basically built by OpenAI, but Microsoft also owns the weights and all weights of the models. So it has rights to retain the model if it wants to. Okay, so because it was a big investor of OpenAI. Anyway, so we have this GLM, generative language model. This is a Chinese version of, and they're building a Chinese version of ChatGPT as well. They are calling it ChatGLM. The model is available on Hugging Face. It's from the Tsinghua University. One of the professors named Jie Tang, and I had the opportunity to meet him in person when he came here for a talk. And I would like to invite all of you to participate in a hackathon that we are going to organize later this year, probably in October. I'll send you the links, and if possible, you can join there. So we'll We'll do something with language models. We'll be trying new ways of building language models or using them. Okay, so that is going to be exciting. And then in 2023, early this year, we have GPT-4. GPT-4 is the paid version of ChatGPT, so it's under a paywall, and it's much larger than GPT-3 or 3.5. Okay. Then we have the Llama model by Meta. Meta is formerly known as Facebook. The Llama model was leaked after just a week of its release. So it was released in February 2023, so this year, and the source code and the weights were released. Okay. Then we have Bard by Google, and then we have a series of models, very recent models actually, Alpaca, Vicuña. These are all built on top of the Llama architecture. Okay, so Alpaca was trained by Stanford, Vicuña by Berkeley and 3 other universities. Again, Berkeley came up with new language models, Koala and Gorilla. Okay. So the public leak of Meta's Llama model was a big event in the community of research. Okay. So the model was released in February 2023, as I said, and within a week, it was leaked via BitTorrent. It released 4 models of different sizes, 7 billion, 13 billion, 33 billion, and 65 billion. 65 billion is the largest model. And in comparison, ChatGPT is of 175 billion parameters, okay? So this is less than half the parameters of ChatGPT, but as we will see in the next slide, it performs quite well. Oh, of course, they do not use 65 billion parameters now. Anyway, so these are the performance of the famous language models as of April 2023, this year, okay? Relative performance over 8 tasks was measured and average to give this performance scores and compared to GPT-4, the OpenAI ChatGPT version, which is the paid version, okay? GPT-3 has 175 billion parameters. GPT-4 data is still not released, but expected to be a lot larger. But I have heard rumors that it could be in the range of tens of trillions as I said. So those are leaked news, not reliable, but still. In comparison, Llama 65 billion was trained on 2048 GPUs for 14 days on a large number of tokens. Okay, if we look at the graph, you can see this Vicuña model. Okay, so this is a model released by Berkeley, trained by Berkeley and released by Berkeley on top of the Llama architecture. So this is a very, very recent model. Okay, I think not even a month old. Okay? And this 13 billion model. It performs 92% as good as the ChatGPT performance. Okay. How do we measure this? This is a human perception. Okay. So this is not a very reliable measure, I would say, but still it performs quite good. Okay. So as of 2023, we can see that smaller language models perform very similar to large language models. So I'm very skeptical of the fact if that Moore's law of increasing model sizes exponentially with time would continue or not. And some of us argue as researchers that even commercial big IT companies are on the verge of like exhausting their resources for training these large language models. So it's not feasible to train much larger model now. Okay. All of these models can be downloaded on Hugging Face. I mean the smaller models, not Bard or ChatGPT. Bard is still not open source. Okay. No compute barrier to research large language models. So you can download this model today, right now, and you can run this model on your computer. Not this, the quantized version. I'll talk about that. And you can start researching. Okay. Okay, so what are the problems and what are the future directions of improvement? As you can see, they have huge memory requirements. Okay, and that's why they require huge amount of energy to train, and also it requires costly infrastructure to train and run them. So those are the main problems, and those problems can be solved by big IT companies because they have a lot of money and power. But we as researchers or academicians have a problem because we cannot afford that much amount of infrastructure or memory. Okay, so what's the answer? So we have twofold answer. Okay, the first answer is okay. Bear in mind these answers are my opinion, so it's not a still proven thing, but still works going on in the research. So analog computing might be one of the promising directions we can go. Startups such as Mythic AI, you can look it up. I have given the link below of their website. They have already created a inside chip, okay? 1 inch cross 1 inch, very flat chip. I've seen that chip that can perform the same number of matrix multiplication using just 3 watts of power instead of 100 watts as required for uh, a digital graphics processing unit um, that can do this same number of matrix multiplications. So why matrix multiplications? Because most of the tasks that we do in AI and machine learning boils down to this matrix multiplication problem. Okay, so if hardware can do matrix multiplication efficiently and faster, those are the hardwares that we need for AI. Okay, if analog computing can do that for us, we can use it. So what's the problem with analog computing? Why we discarded it in the first place? We discarded it because it's not mm, reproducible always. So it has errors. So every manufacturing unit will give us different results. But for AI, we have that headroom. Let's say there's a task where we have to differentiate between rabbits and dogs. It doesn't matter if the model is 97% confident about if the image is a rabbit. It might be 90% confident about the fact that it's a rabbit, and that's still useful for us. It doesn't matter. So as we have that headroom, we can use analog computing for AI. Okay. Can anyone say how much time do I have left? I can keep some of the things. I don't think I have much left. Anyway, so another thing is quantization of models, which can be readily used now. So I'll be showing my live demo using the quantized model. So what is the quantization of models? It's basically reducing the precision of the language model. So if we are talking about the parameter sizes of language model, each parameter is just a floating point number, which holds 32 bits of memory. We can reduce the precision of these numbers hugely to as low as 4 bit. Okay. So consider what is reducing precision mean? It means, let's say we have 10 by 3. How do you represent 10 by 3 in decimal? 0.3333, and it goes on forever. Okay. So instead of writing 8 threes after the decimal point, we write 2 threes after the decimal point. Okay. And that's an approximation. It's still the same number, but less precise. And we have a paper that does this in a specific way. So you do not reduce precision of every parameter, but more than 95% of the parameter, they're reducing the precision for. And they have a paper called GPTQ, and they are shown to be still performing quite well. And using quantization, they are using Llama model on a smartphone like Google Pixel. And they're also using Llama model on a Raspberry Pi. Raspberry Pi is a very small computer that runs on your phone's adapter charger. Okay, so it's very small computer. So we have possibilities. Do I have the time to show the live demo? That is what I'm asking. I can easily skip this part. I think I should skip this part anyway. So I was about to show you a live demo of this Vicuña model that I have installed in my computer. I have a web UI. You can check. I have given the links here. You can install the web UI from this link. It's a GitHub link. You have to know a little bit of Python, okay? And then you can download the Vicuña model from Hugging Face. I have also given the link, okay? So the original 13-bit model, 13 billion parameter model, requires a 64 gigabytes of GPU memory, but after the quantization, it requires about 8 gigabytes. So it's 8 times lower. Yeah. So these are some of the questions that I have already asked the model. So let's see how it performs. So if I ask the model, define large language models, the Vicuña model, the 4-bit quantized models, gives me this answer, okay? Which in my opinion is a pretty good answer. It defines what large language models are. Not exactly, but yes. So it gives some examples, very good examples. Let's look at some shorter answers, okay? If you look at this question, does Himalayas have the highest peak in the world? And in which country is the peak located in? Okay. The answer is yes. Mount Everest, which is located in Nepal, is considered the tallest mountain in the world, and it's part of the Himalayan range. It stands at a height of 8,848 meters and so and so feet. Okay. If you notice, some of the answers are large and some of the answers are so precise and short, and it's very good. Unlike ChatGPT, which keeps blabbering on forever, if you have ever experienced that or used it. What season it is in Australia during January? In January, Australia experiences summer. That's simple, precise, and the right answer. What does Indian youth need to follow to make the country a new global economic leader? I'm not going to read this entire thing. Anyway, it's giving a very generic and correct kind of answer. Okay, that's the point. So what are the conclusions? Large language models are likely to become ubiquitous in the next year. By ubiquitous, I mean they can be seen everywhere, like being used in every field. Okay, LLM-based applications are being rolled out commercially now because big IT companies like Google or Meta, they move fast and break things. That's their property, and they fix the things, fix the mess to society later. So that's a problem for us that we need to deal with. But large language model government regulations can be brought about, but they will likely follow 2 or 3 years later. Um, that's just a hunch. It might take longer even. Large language models will change the meaning of authorship. So by authorship, I mean copyright or information property rights, things like that, because it's easy to generate high quality text. You can write poems, you can write stories, you can bring about anything creative. Okay. Even multimodal models can create audio visual content. Okay. It can create images. Recent models can even create videos, like not just deep fakes which replace faces. It can actually generate the entire video. Okay. The background, everything. And the video is not indistinguishable from humans yet, but the pictures and the text can be. And maybe in future, the videos will be as well. On the positive side, large language models can be enabler for human AI collaboration. And there are examples of such collaboration. Microsoft Copilot, which is built in Visual Studio, the paid version of Visual Studio, not the free version. They have this AI code generator. Okay, so the AI will write codes for you, and you as a human can review the code, and then you can, what do you say? Then you can change the AI code. Okay. LLM-based search, that is language model-based search, is already being used by Google and Bing. So if you have noticed, if you type a question in the search bar nowadays, the search results gives you the answer if it's a well-known answer, instead of showing all the links that contains the answer. Okay, that's one of the utility. LLMs will change education. This might be very relevant for professors and teachers who are in the academic field. So what's the problem? The problem lies in the way we examine students. Okay, we use good writing as a proxy for thinking and depth of knowledge, but that is not true anymore. Any language model has much more knowledge than any single human on the planet, including me and you. Okay, because it has gone through much more books, much more topics and articles that I've ever read, or you will ever read. Okay. State-of-the-art 2023 MIT experiment using GPT-4 plus manual prompt on 30 subjects, including maths, electronics, computer science, etc., for exam and coursework assignments. They show that the solve rate was from 10% to 73%. Of course, 10% is not good enough, but for easy subjects, okay, easy subjects or easy questions in a difficult subject, they perform quite well. And they have withdrawn the paper. It was earlier available here earlier, but they have withdrawn, citing that it's causing reputation damage. And the withdrawal statement can also be found here. So language models' ability to generate human quality content at scale will be dangerous. So you can create like thousands of pictures or thousands of textual content like storylines or poems at a click of a button. Okay. And that is not yet realized by scammers, I think. Order of magnitude higher number of scams will come in the future. Fake news, hard to detect spam messages, even bots running entire social media pages. Okay. So you have to be very careful about what is fake and what is actually created by humans. And we do not have in place systems to detect those. That's that's the worst part. You as humans have to judge just by looking at it if it's created by some language model or not. Let's say you ask your students to submit an assignment and you suspect that it was written using one of the language models, but you cannot prove. You don't have any proof, okay? And you cannot verify if it was true or not. If the student denies it, you have nothing but give him the marks or her the marks because the answer was correct. Okay. So that's one of the problems. And many are not aware of the implications of this fast moving technology, especially elders. So it is our duty to inform our newer ones, especially the elders who are not accustomed with the technology, about the implications of this new age. Okay. So thank you for your attention, and you can fire away any questions that you have.
So I would like to thank Dr. Arpan for his valuable time and from his valuable efforts, we came to know that how well he has explained the whole NLP and various tasks in the NLP and what is a language model and how it is different from large language models and what are the various shortcomings that we are having. And finally, we are having also we are not able to just look at the demonstration part as well, but he has explained it very well. What are the basic requirements for all these? And I would like to thank you, Dr. Arpan Mandal, for your valuable time. And I would also like to thank you all the participants around the world who have joined us for this first session. And I hope that the session is quite valuable and has its own importance. So this is all for today's session, and now we are going to share a feedback link for all the participants, and they have to just go through once, and after that, if you have any questions or queries regarding this session, you can please post it in the question answer box, hopefully, or you can ask anyways. Any questions from the participants?
I think it's pretty interesting, this topic, and I think you should ask some questions about this, because the models that I discussed today, the last few models, including Llama, are very, very recent, and I don't think all of you are, I don't think most of you are aware of those models. So you can fire away any
Exactly,
questions.
sir. Exactly, sir. Yes, sir. These are models very new to us. Any questions from the participants? I think if they still have any questions, sir, can you please provide the email so that if our participants has any kind of queries, they can catch you easily.
So you are asking for the presentation file?
For the email ID, sir, for your personal email ID, so that
For the
they
email
can
ID,
send
yes.
you any query
Should I
IDs.
write it
Yes.
in the chat box?
Yes, sir. Sure, sir.
Okay. So I have two email IDs. Okay, so someone has asked, as teachers, how can we check if a content submitted by a student is actually created by ChatGPT or something similar? So as I said, it's not possible for now. There's no foolproof way to verify if it's been created by ChatGPT or not. It's up to human judgment. Okay, so it's up to us to understand. And if there's no specific system or way to detect or verify this, so that's a problem. That's a very big problem, actually.
Okay, sir. Thank you, sir. Any other questions? So no, sir, there is
Someone
one.
has asked, please provide material for those models you discussed. So they are available on Hugging Face. I'll be sharing my presentation in a different format, in a PDF format. Maybe you can ask the organizers for the presentation file. I think it has all the links that you need for resources. Yes.
Okay, sir. Thank you. Thank you, sir. Thank you so much, sir, for your valuable time.
Thank you.
And thank you all the participants for today's session. And tomorrow we are going to have another session, which is on machine learning and deep learning by Dr. Samita Viswas from Indian Institute of Science and Engineering and Technology. So I hope that all of you have gained much from this session. So we are ending up here for today's session. So I'm going to forward this session towards. Okay, we are going to end this session. Thank you, sir. Thank you for your valuable time, sir.
Thank you.
Shall I thank you so much.
Shall I? Thank you. Shall I leave the meeting now?
Yes, sir. Sure,
Yeah,
sir.
thank you, sir.
So all the participants, we are going to provide you a link for the feedback form.